So I think the easiest way to see how this works and why we care about this is, let's do an example of an EDTA equilibrium. So let's say we have a solution of calcium of 0.10 molar calcium Y2 minus, and some small amount of calcium will be present that's not complexed, right? So there's free calcium ions. This is similar to how, in a saturated solution with a precipitate, you'll have a small amount of the ions that are present that made the precipitate, right? So just like our solubility products. So the question is, how much free calcium, and how will this depend on pH? All right, so if we have a pH 10 solution versus a pH 6 solution. Okay, so the reaction we're considering, just to remember, is calcium 2 plus any form of EDTA in equilibrium with calcium Y2 minus. All right, so at pH, so what we need for what's going to be different between these two is the value of alpha Y4 minus. Okay, so at pH is equal to 10, alpha Y4 minus is equal to 0.3. This is from the table that I showed earlier. At pH 6, alpha Y4 minus is significantly smaller. It's 1.8 times 10 to the minus 5. So a very small amount of EDTA exists in the fully deprotonated form. So from those, we can calculate values of Kf prime. First of all, log Kf for calcium, if we again go to the table, is 10.65. Okay, so if we want to find the value of Kf prime, again, it's alpha Y4 minus times Kf, which will be equal to 0.30 times 10 raised to the log Kf, not pKf, but log Kf. If we plug that into our calculator, we get 1.34 times 10 to the 10. So again, it very much favors the complex here. At pH 6, we can do the same calculation, but of course we're going to get a smaller value because alpha Y4 minus is so much smaller at pH 6. So again, times 10 raised to the 10.65, and we get 8.0 times 10 to the 5th. So a 5 order of magnitude change. Still very much favors the complex, but not nearly as much as at higher pH. And so this is the effect of pH. And if we go to low enough pH, right, at pH 0, we essentially won't have any complex, right? So there's this trade-off in pH. Right, so let's look at what's happening at equilibrium. So coming back to our reaction equation here, calcium 2 plus EDTA, forming calcium Y2 minus. All right, so we started with 0.1 molar of calcium Y2 minus. That's what it says in the problem. Some of that is going to go to the left and form calcium 2 plus and EDTA separately. And so we can say we'll have plus X and plus X here. So I'm kind of put a whole ice table into just one line here. But what we can then use the definition of Kf prime and say, okay, we have the complex on the top, the concentrations of calcium 2 plus and EDTA on the bottom. So we can say we'll have 0.10 minus X divided by X squared. Now this looks a little bit different than our acid-base equilibria because of the way that the equilibria is defined. So things are backwards of what you maybe are used to from acid-base chemistry. Okay, so then we can plug in the values of Kf prime that we have here. So 1.34 times 10 to the 10 for the pH 10, for example, and then we switch that for the pH 6. And so we get that X is equal to, which just as a reminder, this is the concentration of calcium 2 plus. The free calcium 2 plus is which is what we're after. 2.7 times 10 to the minus 6. This is the pH 10. And we should expect a higher concentration because Kf prime is smaller at pH 6. And then at pH 6, we get 3.5 times 10 to the minus 4 at pH 6. Okay, so we can see a 2 order of magnitude change as we change the pH from 10 to 6. And if we kept going to a lower pH, we'd see an even bigger change. So this is an example of how we can set up an equilibrium and how the pH dependence matters a lot in terms of what you get for your final answer, in terms of the value of free calcium that's present in solution. So we're going to extend this to looking at, as we do a titration, what happens with the equilibria as we go along this process.